All right, so now after going really deep into geometric optics, we're going to transition to not geometric optics. So we know that with certain physics principles, it's best to analyze light as rays, right? So our treatment of light as rays and ray diagrams was really helpful in figuring out how light reflects and refracts and how it's handled, thereby in lenses and other complex optical systems in geometric optics. But it turns out that not all physical phenomena that we observe of light can be explained by just treating it like a ray. There are some things that we observe that require us understanding that light is a wave, which is something that you've already learned. Light is electromagnetic wave. And so some optical phenomena require us to consider light as such, as a wave. And so we're going to transition from one regime to another. And, depending on context, it's helpful to treat light in one way or the other. And so now we're kind of transitioning to the things that we observe that require light to be understood as a wave. So going back, we actually introduced the concept of interference before. And so you might be thinking, what's going on? We kind of already know that term. Now there's a whole chapter devoted to it. But it's essential in optics to kind of understand, instead of just the abstract concept of light, of waves overlapping and interfering. There's some specific things that we observe that's kind of neat. So we did cover interference at the beginning of the course with transverse waves. And that same idea applies, of course, to light. So when waves interfere, that means they're overlapping. The resulting wave is the sum of the two waves' amplitude at each point. And it depends on both the amplitude of each wave as well as the phase that each wave is in relative to each other. So one complication that comes along with light that you may not expect is that while it's easy to produce mechanical waves of a single constant wavelength, something that we often consider, it turns out that it's actually quite tricky to do this for light, for optical waves. So producing light that is all in the same phase with itself, coherent, is a particular challenge. Lasers do a pretty darn good job at this, but they're still not perfect. And there's a deep study into improving the design of lasers and making better lasers. And better, typically one metric that translates to a better laser is a more coherent laser. So more of the light is all on the same wavelength and coherent with itself. So there's something called a coherence length. And it's a finite length with lasers that is a measure of the distance that the light travels from the laser source before it becomes completely decoherent. And the wavelength of light that a laser produces, it can drift higher and lower wavelengths within kind of an appreciable range over time. And so there's ongoing work to make lasers better in those specific ways. But anyway, we're going to talk about interference. So we're going to go from this to this, right? And we're going to consider coherent sources. And that's, like I just said, a little bit harder to achieve in reality, but we can get pretty close to the point where you still see these phenomena. So we're going to dive into interference and coherent sources next.